Hi, I'm Bob Fourer, and I'm giving this presentation about software called AMPL that's very useful for optimization problems. These are problems of minimizing costs and distances, maximizing profits that show up in a wide variety of applications, which I'll mention some later. And in order to do this effectively, you need the right sort of software. And what I'm going to do is to go through how AMPL is really appropriate for this kind of software and is really designed to make it easy for you to get going and to successfully build an optimization application. Now, as you can see in this outline, I'm going to do this in three parts. I'm going to start by just talking about approaches to mathematical optimization generally, and I'll contrast a method-based approach to the model-based approach that we use in AMPL. And then I'll look at model-based optimization, and I'll contrast a programming language approach to the modeling language approach that we use in AMPL. And then finally, I'll talk about modeling languages, and I'll contrast an executable approach to the declarative approach that we use in AMPL. So let's start with mathematical optimization. Here you see I googled optimization. You can see that when you Google optimization, what you get is a Wikipedia page of mathematical optimization. And with Wikipedia has a long definition of mathematical optimization here. And let me just highlight some parts of it. They have several definitions of it in the first two paragraphs. There's also a more mathematical definition here, maximizing or minimizing a real function by systematically choosing input values. But they also have some more practical definitions, selection of a best element from some set of available alternatives with regard to some criterion, finding best available values of an injective function given a defined domain. And both of those are correct. When I talk about mathematical optimization here, I'm going to talk about practical optimization. And this occurs where you have a need to make many interrelated decisions many times. These may be purchases, production, shipment amounts, assignments. And you need to consistently make highly desirable choices of these things. So you don't want to choose your shipment amounts in a way that's going to be very inefficient. And you want to do this by applying ideas for mathematical optimization, both ways of describing problems, which we'll call formulations, and ways of solving the problems, which we'll call algorithms. And when you do this in practice, there are large numbers of decision variables. So the things that people are interested in, there are thousands to millions of different decisions, little decisions to be made that make up the overall decision. There's some objective like cost or profit that you're trying to minimize or maximize. And there are various types of constraints, restrictions on decisions you can make. And there are not so many different types of these, but the total number of restrictions overall may be also in the thousands to millions. And each constraint is fairly simple. There are only a relatively few variables involved in each constraint, but they tie all the variables together. And you intend to solve this many times with different data. So you can't just know what the solutions are going to be in advance. Okay? You don't know next week what the data is that's going to come in that's going to require the decision. So you really need some sort of automated process. And the only way to do this is by computation. So there's no way to just sit there and figure it out by hand that will be at all useful for such complicated problems. So you're going to use a computer one way or another. And now what's the process like? Well, typically, if you want to build one of these optimization models, you start out, you communicate with your client here, and you build some model or some method to do it, and you prepare various data scenarios, you solve some cases, you analyze the solutions, you report some results, okay? But that's not the end of it. You don't just get some results and you're done. What you really have is a cycle, because when you report the results, then you go back to the client, and the client tells you that, well, you haven't got it right yet. And there are some things you overlooked. There are some things the client forgot to tell you. There are some deficiencies in your model that are getting you solutions that weren't desired. And so you have to go through this cycle typically quite a few times before you get something that you can come out with and use. So the goal for an optimization modeler is to repeat this cycle quickly and reliably to get results before the client decides that they've lost interest. You're not getting anywhere. And then once you have repeated the cycle reliably and the client is satisfied, you need to deploy this effectively for applications. So goals for optimization software are fast prototyping, okay, easy integration with decision systems, and successful long-term maintenance of the application. Okay? And these are the things that we had in mind when we designed AMPL. Okay? So now let's look at optimization, mathematical optimization generally. Okay? And I'm going to contrast two approaches. A method-based approach where we program a method or algorithm for computing solutions, to a model-based approach where we formulate a description or a model of the desired solutions. Okay? So the question is, which should you prefer? And to answer that, we have to look more carefully at these things. Really, for simple problems, any approach could be easy. So if all our problems were very simple and they only had 20 variables, then I don't think it would matter all that much. But in real optimization problems, the trouble is that they're more complicated than that, and they need to be revised, as I mentioned, to get the formulation right, to address new requirements, to address new circumstances. And in order to do all this, now there really is a difference between these approaches. So here's an example that I'll use to illustrate this. It's a network flow. It's optimal shipping of a number of products from some places to some other places. The motivation is just to ship them efficiently to meet demand. So efficiently is the objective, minimum cost, and the demands are the restrictions. And here's a little diagram to show you what a transportation network might look like. Their cities are represented by these circles, and the arrows are like roads or transportation sources. And so the idea is that you could go from here to here to here, and here to here to here, and so forth. And supplies are represented by green arrows at these nodes coming in, and demands are represented by red arrows going out from those. So we have to take the supplies here and somehow move them around or across these arrows to meet the demands. And they're also not shown here. These arcs have capacities on how much you can ship, and there are also costs on them, and we're trying to minimize the total cost of all the shipping that you need to take in these supplies and meet these demands. So we want to decide how much of each product to ship on each arc so that shipping costs are kept low. The shipments on each arc respect the capacity of the arc, and the supplies, demands, and shipments are in balance at every node. Okay? So however much you ship in, you also ship that much out. So now we can consider, what would the two approaches be like if we're trying to solve an optimization problem of this kind, just to be concrete. And well, a method-based approach is you program a method to build a shipping plan. So a method is sort of a program that says how to compute a solution. So you figure out a nice way to do it. And there are various methods you could do. You could have sort of an order-driven method. You develop rules for how every order should be met. And then you fill the order by one according to the rules. So it says if there's this much demand for this product at this city, you should first try to meet it from here, and then from there. You have all sorts of rules like that. And you try to meet the demands like that. Another way is to have it route driven. You could say, well, we'll choose a route and a product, and we'll ship as much as we can across there till we run into some supply or demand or capacity restriction, and then we'll ship along some other route, and we'll pick these routes one by one until we've got everything shipped. It's another possibility. Okay? And then once you've done that, you can refine it in all sorts of ways to get a better solution. And you can develop rules for choosing good routes, and you can improve the initial solution in all sorts of ways. People have studied these things like meta-heuristics and such ways of really improving how you're doing that. And you can hope by doing it this way to come up with a more sophisticated program that gets you better shipments. Okay? Now let's contrast that to a model-based approach. In a model-based approach, what you say is, I'm going to formulate a minimum cost shipping model, which says the conditions that a solution should satisfy. But the model itself doesn't say how to find the solution. We'll get to that in a moment. And so we'll identify the amounts shipped as the decisions, okay, the variables of the model. We'll specify equations that they must satisfy, the feasible shipment amounts, what's allowable by specifying various equations. We'll write the total shipping cost as a sum over all the variables. That's an objective. And then we'll collect all the cost, capacities, day supplies, and demands as the data. So we're going to come up with a comprehensive way of describing this minimum cost model, which I'll show you now. Okay? And now, once we get all that, we're going to send this to a solver to compute the optimal solution. So a solver is another program. If you give it a problem in this kind of form, written in this systematic way, then for broad classes of these problems, it can find a solution. Okay? So we're using another program to do the solving. We're keeping apart describing the model from figuring out how to solve it. Okay? Solvers handle broad classes of problems so that as long as you keep your description within one broad class, the solver can handle it. And it also recognizes various special cases, just in case that will speed things up. And these solvers are available off the shelf. They're ready to run. You don't need to program them. People have spent a lot of time making them really efficient, and you can focus on your formulation. So here's a formulation for that problem. I say I've got a set of products and a set of nodes and a set of arcs, which are pairs of nodes. So, an arc is just an origin node and a destination node. And now I have all sorts of data which I can write like this. Uij is the capacity of the arc from I to j. And similarly for supplies and costs, I can write down all this data. That's just describing it, And then I can say the variables, what are they? Well, I'll call it xpij is the amount of commodity P to be shipped from node I to node j for each product and for each arc from I to j. And that's it. And then what do I want to minimize? Well, I take the amounts shipped and I multiply them times the costs, right? And I sum those up over all the possible shipments. That's it. I sum over all the products, I sum over all the arcs, the cost of shipping product P from I to j times the amount of product P that I ship from I to j. So I get this big cost function. Okay? And then there are similar expressions for the restrictions. And there are basically two restrictions. One says that if I sum up all the products shipped on a given arc, the total may not exceed the capacity. And at each node, if I take the shipments in to that node plus the supplier demand that has to equal the shipments out. Okay? So the supply is positive and demands are negative. And so so even if in this short talk I can't go through and explain these in great detail, you can see that these are simple equations that relate amounts shipped to things like supplies and shipping limits and costs. So it's just simple equations that I've written down to describe this. Okay? And that's it. Now I've got my model. And then the idea is that I'm going to send this model to one of these solvers. Okay? Now exactly how do I send this model to a solver? Well, that's what we're going to see a little later in the talk when we get down to things like modeling languages. Okay? But now what I want to go back and say is that it'd be very rare that you just do this model and there wouldn't be any complications. In practice, there are going to be operational restrictions that maybe you didn't think of at the beginning or that someone only pointed out after you ran the initial version. So here are some examples. Costs can have fixed and variable parts. So an arc can incur a fixed cost if it's used, plus a variable cost per unit shipped. Okay? There can be minimum amounts on the amount shipped on any arc. So either you ship nothing or you ship at least a truckload or something like that. And there can be limits on how many arcs are used. So you don't really want to have your shipments be too complicated. You want to keep your actual solution simple. Okay? And for this we'll need some extra data, the fixed cost from I to j, and the smallest total that may be shipped, I'll call that m, and the largest number of arcs that may be used, I'll call that n. So we have to put some extra data in there. And now what's this mean for the two approaches? Well, in method-based, I have to revise or rethink my solution approach because suddenly my solutions have to take into account these additional restrictions I didn't have before. And now I have to update my algorithm, or maybe the algorithm that I had thought of isn't doesn't work so well anymore. I have to re-implement it in some way. Okay? And the challenges then in this example are that now when I put these restrictions, the shipments become more interdependent. It gets harder to identify good routes or to identify improvements to the solution. Okay? So the whole things that seem very simple, very obvious in the simple case, become much harder to do here. And in general, the problem you have with this approach is that even small revisions to a problem can necessitate major changes to the method and its implementation. So this is an unfortunate but widely observed fact that just changing a problem a little bit doesn't necessarily mean that you have to just change your method a little bit. It might mess something up with your method and you have to really redo it. And each problem revision requires more method development. So you have this sort of software development, continuing software development that you have to worry about. Okay? Now contrast that, remember method revisions are frequent. So this is a lot of work. And contrast that with method-based. And what has to be done there? Well, I have to update the objective expression to put in the fixed costs. I have to formulate some additional constraint equations to add on those restrictions that I had. And I have to send it back to the solver. And that's it. Okay? I don't have to actually come up with any new method. I don't have to decide how the solver is going to solve it. I just have to adjust the formulation within the same problem type. And what are the challenges for this example? Well, there are new variables and expressions that I have to add, and some new constraints for various things. Okay? But those are the main challenges. And in general, the formulation does tend to get more complicated, and if it gets too complicated or too different, a new solver type or some solver options might be needed. Okay? But it's easier to revise formulations than methods. Formulations are not programs. Okay? They are much more straightforward. They're just a description of math. Okay? As we'll see, a modeling language pretty much describes the math that I already showed. And so all the complications of programming are left to the solver programmers. And you don't have to be a solver programmer. You can just acquire the solver. So that's the difference. And fortunately, a few solver types handle most cases. So you don't have to look at many different kinds of solvers to find ones that work. Okay. So what's my revised model formulation? You see I've added these extra variables. These say that there's 1 if any amount is shipped and 0 otherwise. And those are going to be the used to add in the reduced costs here. I mean the fixed costs. And then my formulation is these constraints are almost the same as before, except for this y here, and I've added 2 more constraints that say that you must ship at least m if you ship anything, and then most NRX can be used. And so I haven't described exactly what how I came up with all these new things, but you see they're all simple equations. It turns out that adding these restrictions didn't require me to do anything very complicated. They still look like simple algebraic equations. And so that's all I have to do for the model-based formulation. I don't have to worry about a new method. Now, where do people use these things? Well, method-based remains popular in certain areas. Applications of heuristic methods. So there are these methods that people use that sort of they're sort of a framework for a method, but you have to program it up for your particular application. So people who like those things tend to do those. And then some situations are hard to formulate mathematically. They have difficult kinds of constraints or black boxes and so forth, and you may have to fall back on some method. And then there's some extremely large applications that they're so big and they're so central to some organization that it's worth having a whole department full of programmers just to keep them going. Okay? And but I would say that also anywhere you have programmers, well, programmers like to program, right? So it's like, why don't we program this up? But I'd say that that's not a justification for necessarily programming things. In fact, model-based approach has been adopted in many ways. It's found in diverse industries. So because it applies to any problem that can be written in a certain mathematical form, you find those problems all over. So I won't read all these here, but you can see that quite different areas have problems that can be approached in the same model-based way. And these go across many fields. So whether they're in business or engineering or economics, or they're operations research problems, all these problems, you have people working on them from quite different backgrounds. And so you have diverse kinds of users, not only people who studied optimization, but people with technical backgrounds who have no trouble comprehending the mathematical formulation of problems, even though they may not want to program up lots of methods. And now, what do these all have in common? Well, in these applications, you have analysts who are focused toward modeling. Their focus is more on what should be solved and less on how it should be solved. So this kind of split between the model and the solver is really works well for them. Another thing is that there are good algebraic formulations for all of these problems, as I mentioned, and there's an emphasis on fast prototyping and long-term maintenance. So there's that modeling cycle that I mentioned where you want to get prototyped and something working fast, but at the same time you want someone to be able to come back to it and work with that model sometime later when changes need to be made. And so that's my argument, or that's the reason why we decided to focus on model-based optimization and not on methods. Model-based optimization has a lot of attraction in many cases. And so now the question is, well, what are the approaches to model-based optimization, given you want to do it that way? And in order to explain that, I have to say that there are two forms of an optimization problem, and this is really what makes it more complicated than it would otherwise be. There's the sort of modeler's form, which is the mathematical description that's easy for people to work with, and that's the description I presented. But there's also a solver's form, and solvers do not work with that mathematical description. They work with an explicit data structure with a bunch of numbers in it, because they're basically number crunching programs. And so they want quite a different description of the problem, very explicit with lots of numbers in it, and not something that you could read or want to deal with. It's just something that a solver program wants to deal with. And so there are two approaches then. A programming language approach is to write a program that generates the solver's form. So you put all the input into this program, and you have that program generate a solver's form from your model. And the other, what I call modeling language approach, is to write a model formulation in a language that a computer can read and translate. So in other words, write a modeler's form in a computer language, and then have a computer program translate it to the solver's form. So here you write the program to go from this form to this form, from modelers to solvers. And here we have sort of a standard program, which will turn out to be AMPL, that writes the model, that takes a model formulation that you've sort of transcribed into computer language and does all the translating itself. And so I can briefly compare these. If you want to use the programming language approach, your program has to read data, has to compute a lot of coefficients in the objective and constraints, send the solver the data structures and so forth, and then in just the form it wants, and receive the solution data structure, and then figure out how to view things. And there are some attractions to this. It's good for embedding in larger systems. If you write all your enterprise systems in a certain programming language, you could write your generator in that language too. And it does give you access to some advanced solver features that might be hard to get at otherwise. But it has many serious disadvantages. This is a very difficult environment for modeling. The program that you write just doesn't resemble the modeler's form. It looks like a program for coefficient generation. And so you can't just look at it and see what's going on. So that makes it harder to revise it and maintain it. And in a program like that, the model isn't really separated from the data. And as we'll see, that's a desirable thing, to be able to look at the model without having all the data mixed up in there. And and it gives you a very slow modeling cycle. So what typically happens is you write the program and you run it, and the results are clearly wrong. You know, all the shipments are 0, or the solver tells you there's no feasible solution. And it's at that point it's hard to check the program for correctness. Is the problem that you made a mistake in your model? Is it that you got a loop index wrong? Who knows? And it's hard to distinguish the model and the programming errors there. And all you have is that program, and the output is some complicated algorithms form, you know, solvers form that you're sending. So debugging in this approach is quite difficult. And contrast the modeling language approach. Here we use the computer language to describe the modeler's form. As I said, you write your model in this language, and eventually you'll see a whole description in a modeling language of our example. And you prepare data for the model, and then you let the computer do the translation to and from the solver's form. So we've got model, data, and solver separated out in a nice way, and you can continue to work on your model without ever looking at a computer program. And it has some manageable drawbacks, which are, however, manageable. You do need to learn the modeling language. Okay? But you know, it's like math, so it's not so bad, really, as you'll see. You do incur some overhead in translating it, but that is also not so bad, as practice has shown. And you have created now a description of the model, so you have some valuable IP. Okay, your model isn't hidden inside all this programming, so no one can see it. But presumably, you know how to protect IP. And so there are great advantages to this, though. It really speeds up the modeling cycles because you have your model in front of you all the time. If there's an error, you know that the problem is something wrong with your model, and you can go back and run various tests to find it. It gives you more reliable modeling for that reason, and more maintainable applications because you always have that model there to consult. Okay? And so with AMPL, we definitely what we want to do was build a modeling language for model-based optimization. And so what kind of modeling language? Well, the popular modeling languages that people have built for optimization are what are called algebraic modeling languages. Okay? And they use there are computer languages based on algebraic formulations, which are like the one I showed before. So the description here that appeared on a previous slide, that is an algebraic what I call an algebraic formulation. Okay? It's got algebraic expressions, it's got inequalities and equalities, okay? And it's just like the algebra that you see in a calculus class. And it's familiar to people because everyone with a technical background has to take calculus sometime. And at the same time, it's general. It's an amazing variety of problems that this kind of approach describes effectively. And so algebraic modeling languages are really the ones that you see these days. And so that's what I want to move along to the third part of the talk, which is on approaches to modeling languages, and specifically algebraic modeling languages, and ask what approach you should take. And again, there are two main approaches. There's an executable approach where you build a modeling language by simulating it inside a general purpose programming language. Okay? Maybe C++, maybe Python, something like that. And what you do is you redefine the operators like plus and less or equal to return these constraint objects. So you can actually write things that look like constraints inside the programming language, and they're processed in the appropriate way to generate input for the solver. Okay? And the other approach is a declarative approach, which is to define a language specifically for optimization modeling. Okay? And so you make it look exactly like math as much as you can. Okay? And then eventually you extend it with some basic programming concepts just so that you can prepare things for the solver, and maybe call the solver multiple times and test some conditions. And then if you need to embed it in a larger system, there are various APIs for accessing this language and the whole system. So, but you don't try to actually use a programming language to describe optimization models. You use a language that's for optimization models. Okay? So now let me go back to our example and contrast two of these. And what I'll do is I'll show for the executable approach, I'll show something called Gurobi, which is the Python modeling language that comes with the Gurobi solver. Okay? And it makes a good example. It's one of the nicer ones. And and as we'll see, it's based on Python. And the declarative approach is AMPL, which is the language that we invented. Okay? And it's based on algebraic notation and designed specifically for optimization. And it generates problems for Gurobi, as you'll see other solvers as well. Okay? And I'm going to use a really simple network for this one. And the Gurobi example comes straight from the Gurobi website. So we use their data for this. Here. And so remember the formulation. I said that we have a set of products and a set of network nodes and a set of node pairs that are the arcs. And we have three kinds of data: capacity, supplies or demands, and cost per unit of shipment. Okay? So in the modeling language, I'm going to have to specify all this data. And so let's contrast how the two languages do that. So to start with, in Gurobi, I have a list of products, and I have a list of nodes, and I have a dictionary of arcs and capacities, in the special kind of dictionary that Gurobi provides, called a multi-dict. And so you see it's saying here that the arc from Detroit to Boston has a capacity of 100. Okay? So basically I'm defining various Python program variables, and I'm putting the data in them. Now, in AMPL, what this looks like initially is just that. So I say there are three sets: a set of products, a set of nodes, a set of arcs within the node pairs. And then I say there's a parameter called capacity, and there's one for each arc. Okay? Now you notice that in the definition in AMPL, there's no data. It's just a description of the data. Okay? Because AMPL, we knew we wanted to keep the model and the data separate, so you could just look at the model and see what it is you were dealing with without having to look at a whole list of numbers. And the idea was that the numbers would appear in some later file. This shows a text file example, although it can be in other kinds of files like spreadsheets. So later I say what the products are and what the nodes are and what the capacity values are in this table. Okay? And that's a distinction that we can make very strong in the modeling language because we're designing the language. And also we can have various formats. So you may, this kind of dictionary is sort of repetitive. In AMPL, we could say, well, we'll take two-dimensional tables if that's what you want. Okay? So we have more flexibility in what we accept because this is just an input format. It's not a programming format. Now the same thing goes for the rest of the data. So for example, for the supplies and demands, the Gurobi model has another dictionary there. And in AMPL, all you say is that, well, there's a parameter called inflow, that there's one for each product and each node. So that says if it's positive, the amount of product that flows into the node. If it's negative, it's the amount of demand that flows out. And then the actual data is in a table somewhere else. Okay? And then there's a really big one. This is for cost. There's a cost has three indices: the product and the origin and the destination and the amount. You see, you get this huge table of data here. In AMPL, all you say is there's a cost indexed over products and arcs, and then in some other file you have the data tables. Okay? So we can take advantage of being able to do nice sort of three-dimensional tables by slicing them over for one of the indices. Here's the products. And so that's the data. That shows sort of the difference in the data. And now, what about the model? We've got variables. We've got an objective function. We've got two kinds of constraints. What's that look like? Well, in Gurobi, the idea is that this is Python, but you see that here's flow less than or equal to capacity for each arc. See, it can be done so that it sort of looks like a constraint. Okay? And similarly here, the sum of flows plus the inflow equals the sum of flows out, okay, for each product in each node. So you see that they've manipulated Python in a way so that you can write something that's sort of like an algebraic description. Okay? It corresponds, all its parts correspond to the parts of the algebraic description. Okay? Now, if you look in the Gurobi descriptions, Gurobi documentation for this, you'll see that they have a couple of alternatives. There are other ways to do these things. So if you don't, you could do it this way, or you could sum it this way, or you could use this quick sum operator that they provide. And so I want to detour briefly to say why there are these alternatives. Consider just this quick sum. So let me copy that on the top of the next slide. Why do they have this quick sum? Well, there's the description here. This is from their documentation. This is a version of the sum function that's much more efficient. So the problem is that the sum function in Python is not really so fast for big and large numbers of constraints. So they implemented something that would be faster. And even that isn't the fastest approach. And they say you should do it another way if you need a really fast expression construction. So one disadvantage of doing a modeling language inside a programming language is that the programming language might not have been set up to know the best way to generate the constraints, and you may have to work with it in some ways or try some options to get it to do best. Okay? Now, in AMPL knows what are constraints, so it processes them efficiently because it knows it's processing constraints. And so here you see I have a variable flows indexed over products and arcs, minimize the total cost, which is a sum over products and arcs of the cost times the flow, and subject to capacities, there's a capacity for each arc, and it says that the sum of all the flow over all products is less than or equal to capacity, and similarly for the conservation. And what I want to point out is that this is very close. So here's the conservation constraint that I wrote in algebra. And you see that the sigmas have become the word sum, okay? And the subscript ij and a has become ij and arcs, and the xpij has become flow pij, and the spj has become inflow pj. So I've given things nice names, but you see I've basically rewritten this exactly like this. Okay? And there's only one way, there's no quick sum or anything. AMPL processes these sums efficiently. It knows they're sums of things that are going to go into a model. Okay? And so what about solving? Well, GrowPy, then once you're done, you just have, once you've got the everything defined in that Python program, you just have to say m.optimize, and it optimizes the model object m. And then everything else that appears in the example is just to print out results. Okay? That's easy to debug. Okay? And so that's straightforward. It gives you some output like that. It shows the flows that are non-zero. Okay, in this thing. So that's just fine. And what's it look like in AMPL? Well, AMPL you say read the model and then read the data, because they're separate. Choose the solver to be Gurobi and solve. And then solve. So again, it's just one statement really to solve once you set things up. And then you say, okay, I want to look at the flows. When you're developing a model, you want to see things quickly. You can say display the flows, and it gives you a nice set of tables for that. So you don't have to program every single display by just setting a few options for display command. You can get a lot of things you want to look at to quickly see what's going on. Okay? And we can do that because this is specialized to the data structures in the modeling language. Okay? And now, as I said, Gurobi is not the only solver that we support. So if I want to change to the Cplex solver, you see that I've only just changed the name of it, and it solves it. If I want to do the Express solver, it'll solve it, so forth. Okay? And so now I want to just compare these in two respects. What about integration with applications, which I said was important. Once you get your model all running, you want to embed it into a broader system. And the real appeal of this is that everything can be developed in Python. So if you're doing the rest of your system in Python, then there are all these other tools that you could use and just embed this right into Python. And the GrowPy also has similar modeling features in other languages, but not as powerful. In AMPL, you can if when you want to embed it, you can, well, there are loops and tests and assignments that the modeling language has been extended with that let you write some scripts to automate a number of things. And people have written quite sophisticated scripts. But beyond that, AMPL has APIs to different programming languages. So there's a Python API if you want to call AMPL from Python and exchange data with it. And there are APIs for other popular languages as well, and efficient methods for sending the data back and forth. Okay. What about integration with the solvers? Well, GurobiPy works closely with the Gurobi solver. And for some really hard cases where you have to do really advanced things, that can be attractive. It supports all sorts of certain special expressions that Gurobi recognizes and so forth. And so that's somewhat appealing to Gurobi users. Okay? And AMPL has the advantage that it supports all popular solvers, so that you can try out all solvers and not only the so-called linear solvers like Gurobi, Cplex Express, but also a variety of nonlinear solvers which use different methods. And so as I said here, it extends to more general things. So this is quite a more general modeling language, and this can be really useful in prototyping where you want something that works quite generally. Now there are programming language-based modeling languages that support more than one solver as well. I've chosen Gurobi to specialize to Gurobi, but you can find ones that are more general. So now, what about those complications I described? What happens there? I only showed the simple example, right? I want to have, I had to put in those extra constraints and variables and fixed costs. Well, it's really easy to add variables to the model, add a term to the objective, update a constraint, and add to send to the same solver. So when I put these extra things in, I don't create something that requires a lot of reprogramming or anything. I just go into that model file and do some things. I add some data and I'm ready to go. And so rather than show that on a slide, let me go and just show it in action. Here's that revised model. And you can see that here's now the updated AMPL model. And you can see that I have two more constraints: ship at least and use at most. Okay? And I've made just one other update to the constraints, and I've added the fixed cost term here. But doing that was quite easy as a matter of just editing this file and putting in the extra constraints, and the constraints correspond to their algebraic description. Okay? And now I need some data for that, and here I've used the text file for the data. So, oh, there it is. And you can see that there's the data files that you saw. Okay? I've added these two extra pieces of data, the least shipment amount and the most arcs. But there's all those tables that we had. And so I've got the model and the data, and once I've adjusted that to correspond to my updated problem and my revised problem with all the complications, then it's simple enough to solve. So I'll just actually type this in here. There's the model and data net flow rev that data, and I'll say option solver Gurobi, and I'll ask it to solve. And this is still a simple problem, even with all those restrictions in there. And so what do I want to see? Well, like use is 0 if you don't use an arc, and 1 if you do. So if I display use, you can see that it gives me something like that. It's quite flexible. If I really wanted in a table, the problem is it's giving me a list because there are so few of them. So now I can say option display one col, turn it off. Okay? And now I get a little table. Okay? And if I display the flows, it'll give me a little table of flows. And that can be manipulated in various ways too. And you see that here it's got the flows of product 1 and product 2 there. And now if I don't like something, I can display various other things. You can display any any expression that you can write in AMPL. And then I can go back and revise the model and data and try it again and so forth. So then you've seen a bit in action there. Okay. So let me say just a bit to wind up here. Let me say just a bit about solver software. They're off-the-shelf solvers for really broad problem classes. So one solver often works for a whole project, and these are implemented. They're based on optimal algorithms, but they're implemented as very complex methods and various heuristics and combinations of things. So these solvers are not just simple algorithms. They have a lot of sophisticated ideas in them that are useful on a broad variety of problems. And in addition, they check for special cases and handle them efficiently. So these are the results of literally decades of development. And many difficult problems are solved regularly by these solvers with even millions of variables and constraints. Hard problems from a decade or two ago are now easy. So these have really become strong, and they justify sticking to a modeling language and not trying to do any of the solver or the method work yourself. And there are many examples of these. The example of problem we had is what's called a linear or quadratic. In fact, it's entirely linear example that I had. And so there are various good commercial solvers. In addition, there are free or open source solvers. There's a whole other nonlinear class that handles a more general kind of problem, and there are other special kinds that are useful in handling some more difficult situations. And so, but you notice I don't have a whole lot of categories here. Okay? So it's not hard to do this, and with a language that supports many solvers, and all these are supported by AMPL, you can easily benchmark lots of solvers and see which ones do best for your problem. And so that concludes my introduction, and I'd just like to say that there's plenty more about AMPL. If you want to learn more, you can get a demo or a full trial, and if you see the links in this video's description, you'll see a number of other possibilities for getting and trying AMPL that you might want to try out.